Good morning, everybody. So today I'm going to be discussing the defocusing in the extended image domain caused by errors in VTI model parameters. Imaging with an inaccurate velocity model leads to the residual energy appearing at non-zero lags, which can be used to update the velocity model. A lambda x here represents the horizontal space lag. And the defocusing is commonly quantified with the differential semblance optimization and stack power estimates. And here's the formula for the DSO objective function, where the horizontal space lag plays a role of a penalty operator. Image domain wave field tomography has been successfully applied over the last few years. However, almost all existing applications have been done for the isotropic media. And here, as a preliminary step towards building a tomography algorithm, it seems interesting to take a look how VTI model parameters influence the residual energy in the extended images. So, in VTI media, P-wave kinematics is governed by three parameters, which are the symmetry direction velocity Vp0 and the Thomson coefficients epsilon and delta. However, it is possible to use other alternative parameter sets, and the choice of three independent parameters is actually important and depends on, as it was discussed today already, such factors as acquisition geometry. It depends on whether we are going to rely on reflections or transmissions, and of course it depends on which method is going to be used for velocity model update. Here we choose to use the normal moveout velocity for a horizontal interface VNMO and an ellipticity parameter eta and delta. And our choice here for this analysis is based on the fact that VNMO and data are two parameters that mostly control reflection moveout in the data domain in VTI media. It has been studied in detail how each of these three parameters influence the reflection moveout in the data domain. As shown by Tariq and Ilya in 1995, the reflection moveout for a horizontal interface and laterally invariant VTI medium above it is given by this formula. And I would like you to notice two things here. First, eta is present only in the last term. That means that for a horizontal interface, eta influences only the non-hyperbolic portion of the moveout. And the second thing here is that delta is not a part of the equation at all. That means for this model, reflection moveout is not sensitive to delta, and therefore it cannot be recovered just from P-wave reflections. In 2012, Paul and Tariq studied the eta influence in the extended image domain, and they did the analysis for a horizontal interface, and the conclusion was that the distortions, errors in the parameter eta cause the residual energy, the residual moveout that has a particular linear shape. And they mentioned that this particular shape, they call it V-shape, could be used potentially to distinguish the errors in the velocity from errors in anisotropy. Well, however, that's only the part of the story, because if in the case of the dipping interface, the influence of eta on the reflection moveout is different. It actually affects the normal moveout velocity for the dipping interface, and therefore the conventional spread moveout. These two plots show the dependence of normal moveout velocity on eta in the presence of dip. P here is a ray parameter of the zero offset ray, and along the vertical axis we have the normal moveout velocity as a function of the ray parameter, normalized by the dependence for the isotropic case. And plot on the left shows the three curves, three dependencies for three different models with different values of epsilon and delta, however with the same value of eta. And plot on the right shows the dependence for three models with three different values of eta. Now clearly the normal moveout velocity is affected by eta in the presence of dip, and typically if dip reaches 25-30 degrees, a normal moveout velocity becomes sufficiently sensitive to an ellipticity parameter eta. And So what I would like you to keep in mind from all that background review is that the influence of eta on the reflection moveout is different for horizontal and dipping interface. For a horizontal interface, it affects the non-hyperbolic portion of the moveout, but for a dipping interface, it affects the normal moveout velocity and the conventional spread moveout. And as far as the last parameter, delta, is concerned, if it does not vary laterally above the target horizon, then the reflection moveout will not be sensitive to this parameter at all. So, and these two things is actually enough to understand the rest of the presentation. So now let me move on to the methodology. A wave field-based imaging can be described as a sequence of two things: a wave field reconstruction followed by an application of an imaging condition. And optimally, of course, wave field reconstruction in anisotropic media needs to be done with elastic wave equation, which is significantly more computationally expensive and would also have to deal with the issue of the crosstalk between P and S wave fields that would lead to the appearance of the fake mode in the resultant image. And alternatively, wave field reconstruction can be done under the pseudo-acoustic assumption. That's the same equation that Hui already showed us this morning. It was proposed by Fletcher, Fowler, and Dew in 2009. And there are a variety of these pseudo-acoustic equations. In general, all of them accurately describe the P-wave kinematics in transversely isotropic media, but they also produce the shear wave artifact with the diamond-shaped wavefront. We saw it yesterday in the tutorial, and the simplest practical way to eliminate this artifact in pseudo-acoustic imaging is to place the sources and the receiver in the medium where epsilon is equal to delta, which is elliptical medium. So we are going to use pseudo-acoustic wave equations for wave field extrapolation. Sources and receivers for all synthetic examples that I will show you are located on the surface, and the near surface layer is taken to be elliptical for the purpose of suppression of these waves, T waves. We assume that the normal moveout velocity is known, and we'll analyze the images obtained with different values of eta and delta. And we'll use the DSO and stack power estimates, which is a common choice, to quantify the defocusing. And finally, to facilitate the interpretation of the residual moveout in the extended images, we apply the angle domain decomposition. Well, the first model is a simple model. Interface has a horizontal and dipping segments, and the VTI medium, all three parameters are constant above the interface. The actual values of eta and delta field are equal to 0.15. This is conventional RTM image obtained with actual velocity model. The interface is properly placed and well focused. And here, three vertical lines indicate the location of the space lag common image gathers. And this is the order I am going to show you, the CIGs. The horizontal coordinate will increase from left to right. First, let's have a look at the ones for the actual values of eta, which is marked in red. And for the rest of the presentation, if the value is marked in red, that means that's the actual value of this parameter. So here, everything is correct. We keep, as I mentioned before, VNMO to this correct value, delta as well, and here's the actual eta. Events are well focused. But now let's have a look at the understated value of eta. What is interesting here, so in the middle panel that corresponds to the common image gather at the horizontal interface segment, we can clearly see the linear shape defocusing that was discussed by Paul and Tariq back in 2012. However, for the dipping interface segment, the reflection moveout deviates from the V shape and resembles the one caused by inaccuracies in the velocity model for the isotropic case. And this is explained again by the fact that for a dipping interface, eta affects the normal moveout velocity and the conventional spread moveout. But for a horizontal interface segment, only the non-hyperbolic portion is affected. And the same story here is overstated value of eta equal to 0.3 except for the fact that events curve up. But essentially, yeah, again, V-shape for a horizontal part, and for dipping segments, we have something stronger. And let's have a look at the angle domain common image gathers. These are for the actual model, and they're flat. These are understated eta equal to 0, and the same we can see here. So for the horizontal interface segment, their residual move out is restricted to the large angles, but which represents again the fact that non-hyperbolic portion of the move out is affected. But for dipping interface segments, all phase angles are affected. And these are overstated values of eta, showing the same behavior. So from this simple example, what I would like you to remember is that influence of eta, the signature of eta in the extended domain, is dip dependent. And in order to emphasize that dip dependence, let's compare the two DSO objective functions computed from single common image, from single space lag common image gathers for a dipping interface, which is in red, and horizontal interface in blue. And clearly, again, the errors in eta cause much stronger defocusing in the presence of dip. And these are objective functions, DSO and stack power, using not just single CIGs, but the whole extended image. And what you can probably notice that the DSO objective function is a bit asymmetric, and it's biased essentially toward the lower value of eta. And this is a known behavior of differential semblance optimization estimate, which is usually biased toward the lower velocity. And what about delta? So in this model, delta does not vary laterally above the target horizon, and therefore it does not affect neither the reflection move out in the data domain and consequently the residual move out in the image domain, and only thing that is affected is the reflector positioning. This is the RTM image obtained with delta equal to 0, which is incorrect value, and let's compare it with this, with the actual model. But that's the only thing that changes, because everything else, the focusing is not affected, and therefore the shape of the objective functions is not affected at all. That means that delta essentially cannot be recovered from P-wave reflections, they are not sensitive to it, and on the other hand means that number of relative parameters, of relevant parameters reduced from 3 to 2. Delta does not affect the estimation of normal move-out velocity and data. Now, let's consider a bit more realistic model. This model was based on the anticline segment of BP tilted TI model, and it was simplified as follows. The symmetry direction tilt was removed to downgrade the model from TTI to VTI. The normal move-out velocity field was smoothed, keeping only the two strongest interfaces. That was done for the purpose of eliminating all the intermediate reflections. And eta field is taken constant, equal to 0.15 throughout the model. We, however, do not introduce any simplifications to the original delta field in the BP model, which, as you can see here, varies laterally. Again, this is RTM image obtained with actual model parameters, and vertical lines indicate the locations of common image gathers. These ones are for the actual value of eta, and the events are focused. And let's compare this to the understated value of eta. And what we observed in the previous example, in the homogeneous model, the same behavior, the same pattern we can see here for the common image gathers that correspond to the sub-horizontal interface segments, which is the first and third panels. The residual move-out has a mostly linear shape, close to that V-like shape. But for the dipping interface segments, it again deviates from the V shape and resembles the one caused by the inaccuracy in the velocity. And these are angle domain CIGs. They are flat for the actual eta, and there is a residual moveout for the understated value of eta, which again is restricted to only large phase angles for the subhorizontal case, and for the dipping interface segments, it's observed essentially at all angles. Then we repeated the same test, but now keeping delta equal to 0, just to evaluate what is just to see what is going to change due to the errors in this parameter, which is laterally varying here. So first, let's have a look at the DSO objective function for the actual data. For the actual delta, DSO objective function is essentially flat between 0.1 and 0.15, which means that it is biased again toward lower eta. But if we compare this with the DSO objective function for different etas, but with delta equal to 0, we see that neglecting this parameter brings additional errors in estimation of eta. And what I would like you to take away from that example is that we cannot neglect the laterally varying delta field and invert just for the remaining two parameters, because we are likely to end up with additionally distorted values. So if delta field varies laterally, then all three parameters must be included in the inversion. And the deviation of eta signature from the linear shape that was observed in the first example remains valid here for this more complicated heterogeneous model. And finally, let's consider the model with the pronounced spatial variations in the anisotropy field. The VNMO model consists here of two horizontal from two homogeneous layers, and there is an identical Gaussian anomaly in eta and delta, and the maximum value in the middle of the Gaussian anomaly reaches 0.15. So here we are going to keep eta and VNMO to their correct values and play with the values of the strength of the Gaussian anomaly in delta. Oh, but first let's take a look at the shot gather. That's the observed data. Shot is located in the middle of the model, right above the Gaussian anomaly. And what happens here that clearly the laterally varying delta field affects the conventional spread moveout. What happens is the positive Gaussian anomaly in delta, in the case of constant VNMO, creates a negative Gaussian anomaly in symmetry direction velocity. And this is why the shot gather that you see here, and the effect resembles the negative anomaly in the velocity for the isotropic case. Now let's take a look at the RTM images obtained with different values of the maximum value of the Gaussian anomaly in delta. Other two parameters are kept to their correct values. And the reflector positioning is affected due to the errors. But not only this, but also the errors in delta here cause quite strong defocusing in the extended domain, as I'm going to show you in a second. So this time, let's only take a look at one CIG located in the middle of the model going through the Gaussian anomaly. And here are space-like CIGs for different values of delta. Yeah, this is a clear defocusing caused by neglecting the laterally varying delta field. And precisely the same can be seen in the angle domain CIGs. It is flat for the actual strength of the Gaussian anomaly, and for understated and overstated values of the Gaussian anomaly, there is a residual moveout that essentially is observed at all angles. And let's have a look finally at the objective functions, DSO and stack power. DSO objective function has a well-defined minimum. However, it's also asymmetric and biased a little bit toward the larger value of delta, which again corresponds to the smaller velocity after all. And the stack power objective function here is biased clearly toward the larger delta. And what happens here, we have a trade-off between the geometric spreading and the defocusing of energy due to the inaccuracy in delta field. If delta is larger, then VP0, the symmetry direction velocity, is smaller, and wave fields will correlate at the smaller depth, where they carry more energy. So what we see here essentially, focusing is quite sensitive to the laterally varying delta field, but still it's pretty challenging. It will be pretty challenging to recover all three parameters, including delta, just from P-wave reflections. This is probably just not possible. And to sum up, we analyzed the extended images for the VTI models of different structural complexity, and we used the common criteria, which are DSO and stack power. And what I would like you to take away from this presentation is that the eta signature is deep dependent. It comes again from the fact that the influence of eta on the reflection moveout in data domain is different, affecting a non-hyperbolic portion of the moveout for the horizontal interface and the normal moveout velocity and the conventional spread moveout for the dipping interface segment. And another thing is, if in the case when delta field does vary laterally, we cannot neglect it and invert for the remaining two parameters. VNMO in data and delta in this case will have to be estimated jointly, but it will require bringing additional constraints or additional information like a check shot VSP, walkaway VSP, and whatever is available. With that, I would like to thank Paul and members of I-team and A-team for fruitful discussions throughout that project, and I'll be glad to take any questions you may have. Thank you very much.